So, we will continue with the printed wiring board technologies module. We have finished 4 hours in this particular chapter, and if you have observed, what I have basically done is taken you through the basic process steps of fabricating and understanding the technologies involved in the manufacture of a printed wiring board. It can be a simple single sided board or a double sided plated through hole board or a multi-layer board or a high density interconnect structure. But basically what we have seen now is the individual processes have been described, so that these basic processes recur at every layer's manufacture. So, it is going to be repeated if you are going to do a multi-layer structure, and therefore, it is very essential that you know the basics of the key processes that we are now discussing. Now, in the previous talk we have seen about the laminate selection, what kind of laminates you have to choose, the quality of laminates. Then we spent a lot of time on imaging. Before that, we talked about cleaning and preparing the substrate for the manufacture or the imaging process. Then the imaging and image transfer including photolithography was discussed, and now we are going to see how a circuit is now established on the copper surface after the developing process is complete in the image transfer process. If you recollect, we have used dry film or a wet film photoresist, we have applied UV light, and then we have cured the board, we have developed the board, and now the board is ready for the etching process. Now, etching, as the term indicates, is the removal of unwanted or non-circuit copper areas from the board. So, you can see here in this figure at the top, what you see here, the red lines are the copper areas. So, that means this is a typical double sided copper structure. On the top, imaging has been done using, let us say, a dry film photoresist material, and then it has been developed, opened, and then you can see some areas of copper have been etched out. Okay, some copper areas are remaining. So, typically in this particular cross section, what you should understand is that the area behind the mask or the resist is the circuit areas, non-circuit areas have been removed. Okay. So, this is typically depicting the etching process in the printed wiring board sequence. Now, the term etch resist you should understand, because you can have organic and metallic resist. As the term indicates, resist is a term for resisting the etching process. The resist material should not be eaten away or react with the etchant chemical. So, that is why the term etch resist comes into usage. So, you can have an organic resist like a dry film material or a wet film material. Typically, a photoresist material can behave as a etch resist, or you can have metallic resist, right. In the case of metallic resist, typical examples can be tin, which is plated on copper. Then you can have gold. Gold is usually plated after an undercoat of nickel is plated. So, you can have nickel gold plating, which can act as a etch resist. Then you can have other alloys, typically based on silver and so on, but in general practice more than 90% of the etch resist in the classification of metallic resist is tin or nickel gold. The reason why we use nickel as an undercoat of gold plating is that if you directly plate gold onto copper, after some time or during its operation and based on the environmental factors and so on, and also due to the inherent crystal structure and properties of copper and gold, gold can dissolve into copper interstices, and therefore, after some time you will see that the thickness of gold that you have plated is gradually reduced. The reason why we plate gold is because of the good contact resistance, good conductivity, and you need to plate only a very thin film of gold compared to larger thicknesses of tin, for example, if you want to protect copper. So, nickel is known as a undercoat or a very basic essential requirement if you want to plate gold on copper. The thickness of nickel can be around 3 to 5 microns, and gold can be about a micron or less than 1 micron. Now, after the etching process is over, the circuit gets defined, right. You are removing all the unwanted copper. Now, the etchant chemicals are corrosive in nature. Typical examples of etchant chemicals, as you can see at the bottom of the slide, are ferric chloride, cupric chloride, ammonium persulfate, which is a micro etchant, chromic acid and sulfuric acid combination, and so on. For the through hole processes, we also use ammoniacal alkaline ammonia solution. So, these are the basic resist etchants that you will see, and also the etch resist given here, typically organic and metallic. Now, etching is a process which is dependent on time and temperature. If you take an etchant, let us say cupric chloride, you have to maintain suitable working temperatures for this cupric chloride. Then, if you are using machine based conveyorized etching, then there are other factors that come into picture that are based on the equipment, the machine. Therefore, those controls have to be taken care of. Maintenance is a crucial issue if you want to get very high performance etching, and especially if you are doing fine lines, okay, of the order of 4 mils and so on, your etching process has to be well controlled, because time and temperature are going to be closely monitored if you want to etch away a few microns of copper perfectly with very clean edges. But etching normally, whatever be the best controls that you do, etching is not a perfect process. There will always be defects, because it is a very fast process and it is only the resist that protects your copper, nothing else. Process control is required. Therefore, there is a term called undercut. So, undercut issues in etching are very important. We are going to discuss what undercut is. Basically, as the name indicates, if the etchant is going to seep under the photoresist material here and remove copper in those areas which are supposed to be protected, then it is known as a undercut. Undercut can be fairly small in number, or it can be large if your etching controls are not well monitored. So, the idea is you should have minimum undercut on the lines and the pads that you have defined. Now, the environmental question of recycling of spent etchants is not normally well considered, but if you look at the current legislations of the usage of certain chemicals and also the local environmental regulatory body, they will issue guidelines how you have to recycle your spent etchant. But today it is somewhat straightforward. That means, if you buy an etchant from a company A, the company A is willing to take back your spent etchant at a fairly nominal price. So, in that sense, you do not have to do the recycling. The manufacturers themselves are willing to take back the spent etchant. Spent etchant means that you cannot regenerate that etchant any further. So, the next point is regeneration of etch solutions is required frequently, because when you make up an etch solution, the concentration of the basic etchant ions or the etchant free radicals or whatever is generated based on the etchant, it has to be regenerated. Now, the rate of etching comes down slowly as you progress using the same etchant. Therefore, you need to monitor regularly the concentration of the copper that goes into the solution, because the basic reaction of an etchant with the copper surface on the PCB is that the copper has to dissolve into the etchant. Therefore, as the copper concentration increases in the etchant, your reaction slows down, the rate of etching goes down, and therefore, your etch time, which is actually a very key factor in large volume manufacturing. So, the time will increase, which will again indirectly show up in the undercut. Okay. So, regeneration of etch solutions is considered utmost necessary in large volume manufacturing, and typically you are going to make the extend the etchant life, but after some time you will understand that it has been classified as a spent etchant, and therefore, you have to make up a new solution. Typically in large volume manufacturing you will use conveyorized operations, and because etchant chemical is corrosive, you have to take care of the pollution factor and also the safety of the personnel working in the lab or the industry. We have seen in our previous class a very important factor that determines the design for manufacturing aspect, that is aspect ratio, which is defined as laminate thickness by hole dia, and we have seen how a designer needs to know whether a particular aspect ratio in a design can be manufactured or not, because smaller holes are difficult to plate, and therefore, the solution the plating solution will not wet the small holes. Therefore, the reliability is a concern, and we have said that to keep the aspect ratio as small as possible in the range of 2 to 4. Similarly, another key parameter that you have to consider, which is more concerned with the manufacturer here, not really with the designer, is that etch factor is a key issue, because no etchant gives perfect straight cuts. Etching always will have difficulties, you will always observe undercuts. If you carefully look into the microscope of the side wall of the copper track that you have etched, you will always see defects. Therefore, you have to provide an etching allowance of 5 to 8% on the track width. This is where I say designers will need to understand what an etch factor is, or the manufacturer can suggest to designer that if you have kept a track, let us say at 6 mils, you can give an etching allowance of 5 to 8% on the track width, because in case the manufacturer has observed that consistently in his manufacturing he is getting an etch profile like this, what you see here in this picture. The red one is the copper, the top blue one is the mask or the resist. It can be an organic resist or it can be a metallic resist. After the etching process is over, normally we would be delighted to see a perfect cut, but if you look into the microscope, you will see that there is a deviation. You can see that the areas tapering down from the top surface of the copper and extending to the complete width of the copper that you have taken, you will see progressively copper has been eaten away. So, this distance that you see here can play a major part in defining the electrical performance of that particular track. Therefore, if you get an etch profile like this, the extent of undercut, so the copper that is eaten away here is known as the undercut. you have to minimize the undercut. If you minimize the undercut, then that directly reflects on the etch factor. The etch factor is a number that defines the quality of etching of a particular etchant. For example, material like cupric chloride will have an etch factor, alkaline ammonia will have an etch factor number, then ferric chloride will have a number, and so on. So, do not forget to discuss with the manufacturer about aspect ratio and etch factor. They are two very important processes not to be ignored. So, let us try to define what an etch factor is. The ratio of the depth of etch. So, what you see here, this is the depth of etch to the amount of lateral etch that you see, that is the ratio of conductor thickness to the amount of undercut. So, basically it gives us an idea about the extent of undercut that has taken place despite having a metallic resist or an organic resist, which is fairly resistant to the etchant that you have used. If you look at this picture here, you can understand this is a cross section of the base core structure or the FR4 for example. This is the plated copper and you have protected on top with tin or tin lead. This is the undercut. You have to measure it using a microscope. So, how do you look at etch factor? You are not going to look at etch factor every day in manufacturing. If you prepare a new etchant or if you are working consistently with the same etchant, you can do it once in a while. But if you are moving to some new etchant, then you have to prepare a sample, test board, perform the etching and then do a cross section and then into the microscope you go to the exact area where you have observed the undercut, measure the distance and then you know the thickness, right, you know the starting thickness of copper. So, the ratio of the conductor thickness to the amount of undercut will give you the etch factor. So, the etch factor has to be very high, which means the undercut is going to be very, very low. So, that is what you actually desire. So, if as a designer you are aware of this problem, you can give a certain amount of allowance on the conductor thickness. So, you can increase the conductor thickness by 2 to 5% and then really not worry about undercut. Now, we are talking about wet etching where all the problem comes. Wet etching is where the material, that is the copper in this case on the PCB, is immersed into the chemical solution, that is the etchant, and where it dissolves completely in the etchant material. Now, the etch factor is V by X as I mentioned here. If you want an equation for etch factor, you know the conductor thickness and you know the extent of undercut, which is X in this case. So, V by X will give you the etch factor. The etch factor is again different for different chemicals. Coming to wet etching and now to dry etching, where the material will be sputtered or dissolved using reactive ions that are generated in an equipment, typically in a vapor phase etchant chamber. So, there are a lot of differences between using a dry etchant. You can also use a dry plasma, that means in a reactive ion chamber you can create reactive ions which form plasma and then they react with the copper surface and remove the copper from the surface of the PCB. So, that is a dry etching process. There is going to be a lot of difference between dry etching and wet etching. Wet etching is typically very useful, advantageous for large area removal of copper, whereas dry etching typically does not work well for large volume manufacturing and you can use dry etching for prototyping. Now, we are going to look at a video of the etching process and also the final step of removal of photoresist, which has behaved as a etch resist material in this case. The photoresist is behaving as a etch resist. This video has been shot at CEDT. You can see here we have a equipment which uses cupric chloride as the etchant, and typically this is an aqueous based solution. Cupric chloride dissolved in water and other chemicals added, typically an acid cupric chloride. So, you use hydrochloric acid to the required percentages. So, basically this is an acid etchant. You also have alkaline etchants, which we will also discuss later. So, after etching, the important process is to remove the photoresist which acted as a etch resist. You can see here etchant is a very corrosive chemical. Even the equipment that you are using, in this case it is actually a PVC material, even then you can see that the leakages from the spray of the etchant and the fumes that come out from the conveyorized etching machine or the batch etching machine will create a lot of corrosion. So, the personal safety is very important, and also you have to look at how you can save the equipment for extended life. Now, typically in a etchant equipment, you start with the power supply, then you have a conveyorized equipment. In this case, for example, you can see that this particular board is now imaged and developed. So, you can see here the areas that need to be etched are exposed, that is the copper areas here are exposed to the etchant. The pink areas that you see here are the protected areas pertaining to the circuitry. Now, the board enters into the conveyorized chamber, and then typically the equipment will have spray nozzles that spray the etchant, and then finally you will remove the protective photoresist, and then you will get the completed circuit. So, I will switch on this video once again for your attention. Now, this is the stripping chemical, which is basically a hydroxide, potassium hydroxide, which removes the photoresist material. Okay. So, that completes the etching process. Now, let us briefly look into the chemistry involved in PCB etching, that is copper etching. If you take iron ferric chloride, Fe is present as Fe3 plus, and it reacts with the copper on the surface of the PCB, and then you get a ferrous ion Fe2 plus, and Cu goes into cupric 2 plus. So, ferric chloride reacts with the copper on the PCB to give ferrous ions and cupric ions. Now, this concentration will keep on increasing, and you will see that ferric ions, the concentration will keep on reducing. That is why the rate of etching gradually decreases. So, regeneration is required in this typical case. So, what you do is you add a regenerant chemical, which is basically a source of oxygen, let us say hydrogen peroxide. Now, to convert the Fe2 plus to Fe3 plus, so that the reaction can progress further to react with copper on the PCB and then produce the required rate of etching. In the case of cupric chloride, where copper is in 2 plus and it reacts with copper on the PCB, copper 0, and you get cuprous ions Cu plus. Therefore, here again, as I mentioned earlier, you have to regenerate Cu plus to Cu2 plus to start the reaction, or increase the shelf life or they extend the bath concentration of this particular cupric chloride. Now, the problem with ferric chloride in the first case is that Fe3 plus is not easily regenerated from the ferrous ion. Okay. Therefore, and also the reaction between ferrous and the oxygen air is very slow. So, therefore, you have to again here anyway use hydrogen peroxide based supplier of oxygen, so that you can get Fe3 plus and then water. This is a very slow reaction. That is why ferric chloride is very difficult to regenerate, whereas in the case of cupric chloride the reaction between Cu plus and oxygen is virtually instantaneous and you get back Cu2 plus very fast. So, the regeneration of cupric chloride is well understood compared to the complex FeCl3, that is ferric chloride. And also if you look at the recycling process for ferric chloride and cupric chloride, in the spent etchant of ferric chloride you have Fe2 plus and Cu2 plus. Therefore, the removal of Cu2 plus, which is a commodity that is worth removing from such a spent etchant, is going to be very complex, whereas in this case where you have only copper, it is going to be recovered fairly straightforward. Now, at the bottom what you see here is the progress observed, okay, in a cupric chloride etchant. For example, you see here at the extreme left, this is a very new solution of cupric chloride, which is mild green in color. As the time progresses, as you start using the etchant material, you see it becomes dark, and then finally without regeneration you see it becomes black in color, almost brownish black, and this is the time when you have to regenerate the material. So, at the bottom of the slide I have put two very important issues that you need to always look at as a manufacturer: etch rate versus temperature and etch rate versus cuprous ion concentration. What do you mean by this? The etch rate will be dependent on the temperature of the etchant. Typically for cupric chloride, the temperature normally is set at 45 degrees centigrade. So, try to maintain this temperature to get a good rate of etching, whereas in ferric chloride it can be 40 or 39 and so on. So, look at the manufacturer's recommendation or look at some of the industry practices that produce best results for using cupric chloride or ferric chloride. The other important thing is Cu plus concentration. Okay. So, you need to look at you need to monitor the cupric chloride. For example, in the case of a cupric chloride etchant, you need to monitor the copper ion concentration and therefore try to regenerate as early as possible into cupric Cu2 plus, so that your etchant life is extended. This slide will give you some simple illustrations of what kind of etching defects you can see normally in a finished PCB after etching. The first one indicates, for example, here that in this case this is a typical electrical short. Okay. There are two lines and you can see a short, that is a copper not properly etched. One of the reasons could be that a strip of mask or photoresist is present there which you have not noticed, right. So, there is a problem with the developing process during the photoresist application or image transfer, or it could be that it has not undergone the right exposure in that particular area, or there could have been a bubble which basically has affected the exposure and it has got translated finally into copper. Then the next one is these kind of mouse bite kind of structures that you see where copper has been eaten away. Okay. So, this is again a process problem. Then you have islands like this. Fortunately, it is not shorting, but definitely not an accepted standard or an accepted quality after the etching process. I told you before that at every step, whether it is image transfer or etching or developing, you have to have visual inspection. Then you have zigzagging, open areas you can see. Typically these can be due to debris, external debris sitting on your board. So, one clear point that emerges from these kind of defects is that you have to work in a clean room atmosphere or a clean room, and your materials have to be handled very carefully and stored in perfect clean conditions. Then you see a typical example here is zigzagging, again indicates a poor control on your etching process. And then the last one is over etching, that means you are although it is somewhat over emphasized or exaggerated here, but what basically you see here is the timing is not okay, the temperature could be above normal set temperature, and therefore you can see the lines have been thinned down compared to your design requirements. So, finally, a brief summary on the etching process. Etching is removing unwanted metal or material from a substrate. Different etchings can be used for different metals or materials. You can even etch gold. For example, the etchant for gold is aqua regia, a mixture of hydrochloric acid and nitric acid in a ratio of 1:3. Then you can etch copper, typically in PCB using cupric chloride, ferric chloride, alkaline ammonia. You have different etchants for steel. You can even etch glass using hydrofluoric acid, for example. Therefore, etchants can be employed for various materials and metals, and here we are interested in copper. You have different etchants for silicon, right, in the semiconductor manufacturing, that is typically potassium hydroxide is used, and different etching rates for different etchants towards different materials. So, constant agitation, continuous air supply, time, temperature are the key factors for a good etching process. Mechanical etching is basically mechanical milling, right, using a milling machine. Chemical etching or wet etching is always a question of debate, but people are more inclined to wet etching in printed circuit board industry because the volumes are very large and you require a faster rate. Whereas in the case of dry etching, let us say using dry plasma, you require expensive equipment, and typically they are used for small area surfaces. You can also use electrochemical etching in the case of chemical etching or wet etching, so that you can speeden up the process. So, it is somewhat the reverse of a normal electrochemical cell or an electrolysis process, whereas in this case the PCB will be the anode instead of the cathode. Instead of depositing copper onto the PCB, you are going to remove copper from the PCB. So, dry etching, as I mentioned, it can be a reactive ion etching using a plasma or inductively coupled plasma using RF and magnetic field. You can get more isotropic etching using dry etching process compared to a wet etching process. But the key issue here is undercut has to be minimized during etching, and we have seen that it is minimal in dry etching compared to wet etching, but there are ways to get a better quality control in wet etching. Etch factor should be high, which means small undercut. Vertical etching and horizontal etching are the two processes. In horizontal etching, the board is kept horizontal and it is moving through a conveyorized equipment, whereas in a vertical etching the board is kept vertical and it is rotated. So, it is typically a batch process, and you will have sprays from both sides attacking the copper. Isotropic and anisotropic etching, you see in this particular figure here at the right, example of anisotropic etching and isotropic etching. So, isotropic etching is more has a good control, okay, in terms of the smaller undercut that you can observe, whereas in anisotropic etching the rates are different at different areas compared to isotropic etching. Undercut shapes vary with conditions and protective resist. So, you have to be a very keen observer if you want to look at the undercut. So, as you can see here in this figure, this is a isotropic etching and this is anisotropic etching. So, the rates are almost the same if you use an isotropic etching, but that depends on the material also to be etched in terms of the structure of the material and the etchant that you will use for this. This is anisotropic etching and the top surface is the photoresist or the mask. You will observe more isotropic etching in the case of let us say plasma etching, also in the case of silicon KOH semiconductor etching, because there are different structures available and you can use suitable etchants for that. The undercut shapes in the case of PCB etching can vary with the conditions and the kind of resist that you are using. Now, the question is, if etching is going to pose so much problem, can additive technology help in solving problems with wet etching? In the case of PCB, instead of removing copper from the board or more thicknesses of copper from the board, can you add copper using electroplating to the exact requirement in terms of thicknesses and so on. So, that is why additive technology is becoming very popular. You can mask certain areas on the PCB, that is the non-circuit areas, with a metallic resist or a photoresist, and then plate copper onto the pattern areas that you require to the required thicknesses. Final step in the board manufacturing in general terms would be to strip the photoresist, because the photoresist which acted as a etch resist has done its job and now we are going to strip it. You can use aqueous solution, hydroxide based solution, and then you can protect the copper with anti-tarnish treatment. Okay. It is basically a simple dip of the board into a anti-tarnish chemical. A thin layer will be protected, will be used as a protective agent for the copper surface, and that can be removed later if the board is going to be processed into the next stage. Quality assurance, a very key issue at every stage, visual examination at every step. In all the steps that we have discussed so far is very important. You have to measure thicknesses if you are doing plating for every batch, including thicknesses of the plating of the through hole walls, microscopic examination for residues which can affect the board after the etching and before the etching. We have seen etch defects. So, those can be avoided if you look at some microscopic examination, visual examination on the board. Typically before etching, every panel has to be examined carefully before it goes for etching, because at that point of time you can still rectify the board. Test coupons for every batch of boards will usually be made for quality check, because the quality check will define how well your various chemicals are performing at every stage, and that can go as a feedback to the manufacturing process. So, that completes the etching process. Now, we will go into a new topic called screen printing for printed circuit boards. Now, screen printing is a very commercial activity that most of you would have seen. Screen printing of various inks onto various surfaces like your t-shirt, or simply printing your invitation cards, or simply printing inks onto walls or any surfaces to provide a legend, right. So, the same technology can be used for printing your tracks and pads onto the surface of the laminate structure, which contains the copper and the dielectric material, and you cure the ink and then expose the unpatterned areas to copper for etching. So, it is a simple print and etch process. If you adopt screen printing for printed wiring boards, obviously you cannot do fine line circuitry with screen printing. This is normally used for commercial electronics applications, boards which have larger line widths and which obviously cannot be used for high density interconnects, although screen printing can be used for solder mask printing and legend printing as a finishing process in the high density interconnect or any kind of PCB structure, any system level printed wiring board. So, this picture shows you two types of situations. One is the printed electronics and the other is the conventional electronics. The printed electronics are using printing, screen printing as a step in the manufacture of PCBs. It will be low cost because it involves a simple screen printing process. Long switching times, low integration density, large areas, flexible substrates can be used, simple fabrication process. As I said, you simply print and then etch. Extremely low fabrication costs, but the important thing here is it is low end. In terms of performance, it is low end. If you go to high end performance, high end electronics, which is obviously high cost, here you have extremely short switching times, extremely high integration density, small areas can be done, rigid substrates can be used, sophisticated fabrication technologies, new chemistries, new materials, high fabrication costs, because you are talking about fine line circuitry. Screen printing is a technique that uses a kind of a woven mesh, a nylon or a polyester woven mesh to support an ink blocking stencil. So, basically you are preparing a stencil using a screen plastic or a polymeric screen, and using this stencil you are going to do a printing process, and this mesh is called a screen. Therefore, this process is known as a screen process. Obviously, the surface has to be very clean, the copper surface has to be clean, or any surface for any form of printing. The stencil forms open areas in the mesh. That means, in the mesh you are creating an image, and that image will have open and block areas. So, the open areas in the PCB can be your non-circuit areas. The ink areas which go or flow through the mesh can pertain to your circuit, because the next step is actually you are going to cure the ink, and therefore, they will act as a etch resist, right. So, in this process you are going to use a mesh and you are going to image it onto the substrate by printing. How do you do that? You use a roller or a squeegee, and it is moved across the screen stencil. As you can see here, there is a printed circuit board. Before that, I will explain to you what a screen is. You can see that there is a frame of aluminum which contains the polymeric mesh. Now, you create a stencil. Here the word screen printing is depicted here. The areas where the letters are the open areas and the blue areas are closed. Now, if you run a ink from top to bottom using this squeegee here, the ink will flow into the open areas where screen and printing is written here, and it will print, or the ink will flow through the mesh onto the base substrate. Now, what you see here, after the printing is done or after moving the squeegee, you are lifting the stencil, and you can see on the base substrate the words screen and printing have been printed. So, you can use this as an analogy for printed circuit board. So, here you have a printed circuit board, you have the stencil which depicts the copper and the non-copper areas of your design, which needs to be translated onto the printed circuit board. You take the ink and you squeeze it through the stencil. So, this is known as the squeezy, right. It can be a silicone rubber which will have a very sharp edge, and at 45 degrees to the stencil you are moving the ink through the stencil areas, open areas in the mesh. So, the ink will be transferred onto the base substrate, which is the printed circuit board. You will move it only in one direction. So, assume this is the direction of print, you will get the print onto the PCB surface. So, screen printing is a stencil method of print making in which a design is imposed on a screen of silk or other fine mesh material with blank areas coated with an impermeable substance, and ink is forced through the mesh onto the surface or the substrate. It is also known as silk screen, serigraphy or serigraph. I will describe here the complete process steps for a screen print and etch technique. You select the laminate, clean the surface in the normal methods which I have described you, screen print the resist ink followed by baking in an oven, right. So, you use a suitable stencil, image it and then create a mask for that, and then keep the stencil ready, print it. Now, after the baking is over, you introduce it into the copper etchant. So, this will etch copper in non-circuit areas. Now, you can strip the resist ink from the copper areas which protected your circuitry. Now, you can drill the holes for component mounting, protect copper with tin, because as you know copper reacts with environmental oxygen or moisture. Therefore, immediately you have to protect copper with tin or tin lead in the earlier cases, but today we are discouraging people to use lead. So, tin lead, you can do plating also here at this stage, but you can also use a simple tin coating, molten tin on top of the copper surface. Post processes like solder mask, printing and legend printing can be done later to complete the single sided board. So, note here I have emphasized here that screen print and etch technique should be used for manufacture of PCBs only if it is a single sided board. Do not use this technique for double sided board and other processes, because it is not going to work. We have to focus on additive technology there. This is an example of a subtractive process where you simply are focusing your work on removal of copper. What are the defects that you will see in screen printing for printed circuit boards? Board surface preparation is very important. Quality of ink, the flow properties, it should not be too thick or too thin. Look at the viscosity, look at the type of structures that need to go onto the surface and the time taken for drying, what kind of solvent is used there, what temperatures need to be used for curing the material, is there a shrinkage of the ink after curing. If you look at all of these things, you can fix the exact thickness of ink. Right mesh size of the screen or the stencil that you have used. Quality of the squeezy blades. Typically, the squeezy blades have to be having perfect edges, otherwise the pressure of transfer the ink to the surface of the PCB will not be perfect. The angle should be at 45 degrees to the stencil, that is holding your squeezy blade. Right volume and spread over the entire surface for a particular area that you are working with. Ensure that you have minimum wastage of the ink. This will come with experience. Cleaning of mesh and the blade regularly to avoid drying. So, typically let us say in volume production of single sided PCBs, you will use for some 500 boards, and then you will have to remove the mesh, remove the blade, clean them thoroughly and then use them again, or preferably use a new stencil or a new mesh. Clean and dust free environment as always very much required, so that these are not translated to etching defects that we have seen earlier. So, this is again a figure showing you a screen table, a PCB is mounted which holds the PCB, the clear area between the stencil or the screen mesh and the PCB. So, introduce the PCB introduce the stencil onto the surface of the PCB, load the ink and start the stencil, the squeegee towards one direction, okay, using enough force to transfer the ink through the mesh openings, and then lift the stencil so that it detaches itself from the surface of the PCB. So, there should be no ink sticking between the surface of the stencil and the PCB surface. So, that is where you have some experience on the quality of ink. So, we look at a video of a semi-automatic screen printing for printed wiring board applications. You will understand how important it is for the operator or the technician to understand this process. So, this is the mesh that we have seen, and the blade, squeegee blade that you have seen, and this is the semi-automatic printer where you have the squeegee loaded or fitted onto the machine. Here you can see that the ink, in this case it is a solder mask for example, it is loaded onto the screen printing machine. Now, basically you are trying to create a nice hold using vacuum between the stencil surface and the PCB. Now, here you can see this is the squeegee blade mounted onto the screen printing machine. Now, the ink is dragged or pushed through the mesh openings on the stencil onto the surface of the PCB. If required, you can also do a second motion of the squeegee blade in the reverse direction to the original starting point and then finish the process. Now, switch off the vacuum and lift the holder, place holder of the stencil, and now you can see at the bottom there is the PCB surface which has been printed with the solder mask material. Now, this is a photo imageable liquid solder mask that has been used in this particular case. Now, this has covered the entire area, this is the circuit area. Now, you are going to use a mask for the solder mask after this material has been cured in the oven at, let us say, 100 degrees centigrade for about 10 to 15 minutes. Now, you can place a solder mask photo tool and then open up the unwanted areas and remove it by developing. So, the areas, that is the pads and the tracks, or the pads will be open, other than the pads all other areas will be covered with the solder mask material. So, this screen printing is very useful for print and etch process, a solder mask process, or legend printing for printed wiring boards. Now, we can see here pictorially defects that can be observed during the screen printing process. This is the stencil, this is the PCB surface. You can see if you have the controls right in your equipment and the process steps, you can get perfect dispensing of the material. It can be an ink, it can be a solder mask, it can be a white ink for legend printing, or today screen printing is also used for solder paste dispensing during surface mount assembly. So, in this case, this picture typically depicts metal particles embedded in epoxy medium, and what I have basically shown here is a screen printing process for solder paste dispensing onto the lands that have been generated already on the printed wiring board. At the bottom picture shows you typical defects. So, this is a well defined structure of a line that has been screen printed. This is irregular. So, sometimes you get this, sometimes you get perfect lines. So, here what you do is basically you have to check the mesh openings, you have to clean the mesh openings and the stencil regularly to avoid these kind of defects and instead get these kind of prints. This is again saw-toothed. Okay. You can see consistently you get these kind of defects. So, make sure that you get a well defined line or a image after screen printing process. Now, we will look at another aspect of the PCB process. Remember, we have seen that mechanical drilling is a final step in a single sided board manufacture, whereas mechanical drilling will be the first step in the double sided board manufacture. But today with all the advanced methods, we can also drill first for a single sided board and then register your photoresist material and the mask for a single sided PCB also. So, mechanical drilling of holes for PCB. Why do you require holes? You require holes for registration during manufacturing. If you are working on large volume production, you have to register your photo tool to the copper surface of the PCB at various times during, let us say, a multilayer PCB manufacture. Therefore, you are not going to use manual registration, you will do an automated registration. For that you require holes, mounting holes for assembling the PCBs, or in your PCB you would definitely have mounting holes which need not be plated, but these are going to be mounted to your chassis of your product. Stacking holes during drilling. Okay. So, in a CNC drilling machine, the panels have to be stacked and before drilling process, and therefore, you require stacking holes, and holes are required basically to interconnect two copper layers and make them conductive by plating the hole walls of a mechanically drilled hole. So, in our case we are more focused on how to make a hole wall conductive from a mechanically drilled hole of a structure like this, where you have copper on both sides, a dielectric in between sandwiched. You are doing a mechanically drilled hole and you are going to copper plate this. So, we are going to look at how well a mechanically drilled hole can be made suitable in all aspects for electroplating. Double sided plated through hole printed wiring board. In this case, the interlayer connection is very important. The earliest technology was riveting the holes and making it conductive in the olden days. People have also tried filling it with solder, okay, although it looked very immature for us today, but earlier days this was simply a easy method of filling the hole with molten solder and then providing some kind of a interconnection, but never a reliable one. Filling with conductive polymer paste, this is again well utilized today. If you are making high density interconnects where you are making thin inner layers, you can fill the hole with the conductive paste and then polish off the top and bottom area and then get a very reliable conductive hole. But the more reliable one is metal deposition on the hole wall by electroplating methods, electroless and electroplating methods. This was done or brought into the focus by Shipley in 1964, and we are still working on these technologies of electroless and electroplating combined to get a very reliable hole. So, we will discuss more on these aspects in the next hour.